Well, I guess you didn't think we'd be getting another one of these videos so quick, but I need to do that for lesson June 11th, that Thursday, because I'm going to be out of town. I just thought I'd had some, one of the things we missed during this time was some grounding, bonding and grounding and safety of grounding, and I run across a pretty good video of RSD Academy put out, and they explain grounding pretty good. I'd like you to watch that. Then I'm going to show a video on Mike Holt. It's Article 100 definitions and Article 110 requirements for electrical installations. They have 47 questions after the Article 110 chapter, and if you don't get them all answered or can't get to them all, we'll finish them next week. But I'm going to start this video. It's real interesting. The guy does a good job explaining it, and I was impressed with it. So watch this, and then I'll get the other one going after this one.
Hi, welcome to RSD Academy. I'm Bob Duhamel, and today I'm going to answer a question about one of my videos on the nature of ground. And this question comes from the viewer whose name I have up here that I can't pronounce. I apologize. But the gist of the question is, when you're using ground as a matter of safety, how does the current know to go through ground instead of through you? Does it act like some sort of a switch? Well, let's take a look at the circuit in question. And we have just an equivalent circuit, a 110-volt battery that represents the power plant and the generating system and all of that out there that's supplying power to your house. We have a motor, which is an electric drill or some other type of equipment that you're working with. The dotted line represents the metal casing, which is insulated from the wires, of course. And here I am touching that metal casing, and I'm touching the ground. And I have that metal casing grounded also to protect me from a fault inside the drill or whatever I'm working with here. And the ground connects back up to my circuit. This is something I failed to show in the video, but that's important. Thanks for those of you who called me out on this. But that does go back to the circuit to form a return path. It is an important part of the system. Now, the ground isn't special. It just happens to be a very good conductor and ubiquitous. It's all around, so we use that as a return to get back to the circuit and to make a safety connection or a ground to that ground for safety purposes. So we have 110 volts. My motor, my case, it's insulated. I'm touching the case, but I'm safe because I'm insulated from the 110 volts. Everything's going just fine. But what happens if there is a fault? Let's say somehow this gets connected to the case. Some kind of a short circuit, something gets in there, some insulation breaks down, who knows what, maybe some water got in, but I've got a connection there. So the question is, okay, the 110 volts goes to the case, I'm touching the case, the ground is touching the case, we're both connected to 110 volts. How does the current know to go through ground instead of me? Well, the myth is that the current finds the shortest path to ground. And it doesn't work that way. The current doesn't come in and say, there's a high resistance path, there's a low resistance path, I'll take that path. Nothing like that happens. There's no magic involved. It's just another series parallel circuit or another parallel circuit. It has one path here, one path there, and the lion's share of the current is going to go through the lower resistance. But I'm still connected to 110 volts. It is confusing. Why does this protect me? And I think the reason it's confusing is because we're looking at the wrong place. We look at this and we see 110 volts. I'm connected to 110 volts. The ground's connected to 110 volts. What's the difference? Well, we don't want to focus here because the magic goes on over here. When we draw diagrams like this to understand electronics, whether it's looking at Ohm's law, Kirchhoff's laws, or series parallel circuits where we have a battery and some resistors or other components, we always leave out something important that happens in the real world that doesn't happen in our model circuits. And that is over here, we have resistance. If it's a battery, we call it internal resistance. If it's another component or another system, we call it output impedance, but it's always there. So the battery has its own resistance. The generator and wires and transformers and all the stuff that deliver power to your house, they have internal resistance, or we would call that output impedance. We don't want to get into the capacitive reactance and inductive reactance because that's important, but we'll talk about that in alternating current. But we'll just reduce this down to a battery and its internal resistance. So the battery really has resistance of its own. I'm going to put it up here just for illustration purposes. And remember that this is part of the battery. I don't want to clutter it by drawing a dotted line around it or something, but remember this resistance is part of the battery. We can't get rid of it. And everything has this internal resistance or output impedance. So to understand why that makes things safe, let's unclutter this a little bit and just look at what happens. Let's get rid of everything here for now. Let's just put a resistor here. Now let's say this internal resistance, I'm going to make a really high number. Let's make it 10 ohms.
That's just your internal resistance.
It would
of the
really be
wire
much
and
less
the
than
battery.
that, but for illustrating purposes, let's just make that 10 ohms. And over here, let's make this 100 ohms.
That'd be your drill motor.
This resistor represents our tool or whatever we're working with, or it could be almost anything. We just want to look at what happens over here. So don't worry about what this is. We want to see what happens over here as we use current from the system. So right now we have 100 ohms, 10 ohms, 110 volts. How much current am I going to get? Well, it's a simple Ohm's law problem. Current's going to travel in that direction. 100 ohms in series with 10 ohms, that's a total of 110 ohms. You just add them together in series. 110 ohms, if you know your voltage, you divide into it. So 110 ohms divided into 110 volts gives us 1 amp. That's reasonable to run a motor. It might even take a little more. So we have 1 amp going through the circuit. But more importantly, what happens to the voltage right here? We have 1 amp going through a 10 ohm resistor. Now what happens when you have current go through a resistor? Whenever you have current going through resistance, you get a backup of voltage. Here's my trusty soda straw I used to illustrate this with. Now if I blow through the straw, I get pretty much the same pressure inside the straw. We talked about how there's actually a pressure gradient, but let's not get too complicated about this. But the important thing is if I pinch that straw off, causing resistance, now I blow into it. That pressure backs up and becomes higher where the current goes into the resistance and is lower after the resistance. So we have a differential of pressure. And remember, any kind of pressure is always measured as a differential, and voltage is electrical pressure. So it's the difference that matters. So I have a higher pressure here and a lower pressure here. So I have the same thing over here. When I push current through a resistance, I get a higher voltage here than I do here. Now this voltage is pretty much locked in at 110 volts because it's locked into the battery voltage. So if I have a higher voltage here and a lower voltage here, I must have exactly that, higher voltage, lower voltage. So my voltage here is something lower than 110 volts. How much lower? We can figure that out by Ohm's law. The difference in voltage here, and remember we're always concerned about the difference in voltage. Voltage is always measured as a differential. What's the difference between these two voltages? I calculate that out with Ohm's law. I have my 1 amp of current, my 10 ohms. If you don't know your voltage, you multiply. So 1 times 10 gives me 10 volts. So I have a 10 volt loss across here. Higher voltage, lower voltage. 110 volts, I lose 10 volts. I'm down to 100 volts. So by taking that 1 amp of current, my voltage has dropped, so I only have 100 volts across my 100 ohm resistor. Is that going to work? Do I still have 1 amp? Of course I do. It always works out. So let's calculate that out just to be sure. 1 amp, 100 ohms, 1 times 100 equals 100. Ohm's law still works. So I have 100 volts across here, 10 volts across there. Also notice that the voltage is distributed proportionally. I have 100 parts of resistance here and 10 parts of resistance there for a total of 110 parts, 100 parts of my voltage and 10 parts of my voltage. It's always proportional to the resistance in a series circuit. So, what happens if I reduce this resistance? That's like I have my variable drill, I press the trigger, that reduces the essential resistance or reduces the impedance of the drill. It draws more current, goes faster. So let's make that 50 ohms. Let's make that 45 ohms just to give us an easy number to work with. So I have 45 ohms and 10 ohms. That's 55 ohms total. So 55 divided into 110, that gives us 2 amps of current. So now I have 2 amps. What's going to happen to this voltage here? I have more current flowing through the resistor. More current through the same resistance means a greater voltage. So that means this voltage here will increase. So what does that do? Well, this voltage can't change. This voltage must be higher than that voltage. If the difference got larger, that means I'm losing more voltage. So what happens is I have 2 amps through 10 ohms. Now that becomes 20 volts. So now I start with 110. I lose 20 volts coming to here. So now I'm down to 90 volts. That's the key to what happens later on. The more current I take, the lower this voltage becomes. Now let's reduce this down to 1 ohm and see what happens. That's no longer 90 volts, that's no longer 20, this is no longer 2 amps. So now with 1 ohm, I've got 10 ohms plus 1 ohm, that's 11 ohms total. 11 ohms goes into 110 volts, that gives me 10 amps. So now what happens to my voltage here? I have 10 amps through 10 ohms. If you don't know your voltage, you multiply, so 10 times 10, that's 100 volts. So now I have a huge voltage differential. It's like I'm blowing really hard. Now I get a huge buildup in pressure here compared to the pressure here, and this pressure must be higher than that pressure. And once again, when we relate that to voltage, this voltage has to be higher than that voltage. This voltage is locked in at 110, so if I have a greater voltage here, that means I'm losing more. So I started with 110, I lost 100. What's left over? 10 volts. So now, with this 10 amps, I only have 10 volts left across this 1 ohm resistor. Is that going to work? 10 amps, 1 ohm, does that give me 10 volts? Of course it does, Ohm's law. 10 times 1 gives me 10 volts. So now I only have 10 volts over here. So the lower the resistance is here, the more current I get, and the lower the voltage becomes here. We can look at that other ways too. If I push 10 amps through 1 ohm, how much voltage do I get? Remember, we push current through resistance, we get a backup of voltage. If I push 10 amps through 1 ohm, Ohm's law says I'm going to get a 10 volt backup. So I have a backup of 10 volts across here. So we can look at it multiple ways. So the lower I make that resistance, the lower the voltage across it is going to be. So if we look at this now back at the system we had, so now I have my motor back here, my insulated case, I'm touching it, and my ground connection, let's just say that's 1 ohm. It's too high, but this will show what happens for illustration purposes. So I'm safe now because this case is insulated. I'm not touching the 110 volts. But here comes our fault. Somehow we get a connection there. Now I have the 110 volts going to the case. Now I've got a problem. So, but am I connected to 110 volts here? If I were, I'd get about 50 milliamps through me, which would be deadly. But I'm not going to get 50 milliamps, not because the current comes in and says I'm going to take the shorter path, but this 1 ohm resistance combined with this 10 ohms gives us a total of 11 ohms. 11 ohms and 110 volts gives me a current of 10 amps. Now here comes the magic. Nothing going on here is doing anything special other than the fact that this 1 ohm resistor causes my total resistance to be so low that I'm getting 10 amps through the system. The magic is happening because that 10 amps is going through this 10 ohms here. Where is that 10 ohms? That's out in your generators and your transformers and delivery system, all the wires. That's inherent in the system. We can't get rid of it. So that wire coming into your house, looking into it, you see 10 ohms of resistance. But that 10 amps has to come through that resistance. So what happens? 10 amps coming through 10 ohms. I'm going to develop 100 volts across that. So I start with 100 volts. I start with 110 volts. I lose 100, leaving me with 10 volts here. And now I've only got 10 volts across me. So this isn't some kind of a current attractor. It just lowers my entire impedance. Remember, I've got, who knows? Maybe it's a hot, humid day. I'm sweating. I've got really good contact with the case and the ground, and all the factors add up to about 2K. So how much current am I going to get through me? Well, 10 volts, 2K. I'm going to get through me about 5 milliamps. Well, that's not enough to be dangerous. So it's the fact that my voltage is down to 10 volts that makes me safe. So once again, this is not some special current attractor here. Together, we have a resistance of about 1 ohm. Remember, resistors in parallel. How do you do that? Well, we could say, 1 times 2 divided by 1 plus 2. Now we don't need to do that because we know that our total resistance will be lower than our lowest resistance. So 2K in parallel with 1 ohm is going to be just a little bit under 1 ohm. So we're essentially 1 ohm, 10 ohms, total of 11 ohms. So this lowers our total resistance down to 1 ohm, gives the whole system a total resistance of 11 ohms. That gives us our 10 amps. That's the magic. Getting that 10 amps to come through this inherent resistance causes a 100 volt drop, and now I only have 10 volts across here, which is fairly safe. Now in the real world, this might be more like a thousandth of an ohm. What's that going to do? Well, that's going to, with 10 ohms, that's going to max us out at about 11 amps. That's the best we're going to get, because that's going to be essentially nothing in 10 ohms. So we have 10 ohms, 110 volts, 11 amps, and so I've got 11 amps, but it's not coming in and saying, I'm going to go through the low resistance. No, we've got basically 0 volts. So this very low resistance causes so much current to flow through this resistance that it drops my voltage down to nothing. I lose all 110 of my volts there. Once again, 11 amps, 10 ohms. 11 times 10 gives me 110 volts. I start with 110. I lose 110. I'm down to 0. So that ground doesn't protect me by attracting the current. That ground protects me by pulling so much current through this resistance that it pulls the voltage down to nothing. And now I'm safe. And 11 amps, that's well below what would blow a circuit breaker in this particular example. So I can be pulling that 11 amps till the cows come home and it's not going to blow my breaker. But I'm safe. Why? Because I lose all of my voltage across here. So that's why grounding makes things safe. It's not some kind of a current attractor that attracts the current through the ground. I've still got, only have 0 volts here, so I have no current through me.
Yes, it's helped me to.
And essentially 0 volts across essentially 0 ohms. I get practically 0 volts across it. So that's the way it works. Once again, just quick emphasis. I don't get saved because of the myth that electricity seeks the shortest path. I get saved because my total resistance, me and the ground, becomes so low that I get so much current through here. Here's where the magic happens. I pull so much current through this resistance, which is out in the system, we can't get rid of it, that I lose all of my voltage across there. Simple Ohm's law. I take current through a resistor, I lose voltage.
That Ohm's law formula
with 11 amps, I lose all my voltage. I have nothing left here to be dangerous. So I can hold that all day long and wouldn't even know it. My drill wouldn't be working because who knows how much resistance it has. It's going to only have, it's going to have 0 volts across it too. So why is my drill not working? Why is the wire getting hot? So that would protect me though. So I hope that answered your question. If it didn't, or if you have other questions, please ask. I answer as many questions as I can. And if I can't, other people sometimes answer them. And don't forget to like and subscribe and comment and all those things that help me build this channel.
We'll start the Let's see here. I'm going to start the the video, Mike Holt definitions. Let me see if I can get it going. Hope everybody had a good week. It's been a nice meeting the last 2 weeks at class, and I wished I could be there this week, but things come up with me and y'all, but we'll get her back on track. Definitions, Article 100 and Article 110, requirements for electrical installation. That's what we're going to be studying for June 11th, 2020. And if you would, just, like I say, do these and then do those questions, and we'll get caught back up next week. We'll go ahead and start these definitions.
So let's take a look at the Article 100 definitions. Accessible. You'll see later on in 250, Scott, what is it? 250, the accessible. Was it 250.70 or something like that? Somewhere out there, it says that the connection to the grounding electrical conductor is going to have to be accessible.
Yeah, 70.
70. And then there's an exception if you're going to bury it in the earth. So the accessible is what? Not permanently closed in by the building structure or finish and capable of being removed or exposed without damaging the building structure or finish.
Really get this down.
This is real important. Article 100. You have to know your definitions. When you start working in the code book, then those definitions are going to be making a big difference. Let's take a look at the next definition, which we talked about in 90.4, is approval is acceptable to the authority having jurisdiction. So, what is the authority having jurisdiction? It's an organization, an office, or an individual responsible for approving equipment, material, and the installation, or a procedure. See 90.4, which we talked about. We didn't discuss 90.7 because it had to do with the products, the listing of products. But go back there if you need to know more about that. Bonded. Okay, now we're starting to get into bonding and grounding, some of the meat. This is real important. Bonding. Connected to establish electrical continuity and conductivity. So you can see that this raceway has a bonding bushing and a bonding jumper connecting this raceway. And I can't even think of an application. Well, maybe in a hazard classified location, that would be required. Okay, that's bonded. We even have a bonding type lock nut here. So I guess in a hazard classified location, I have to make sure I look at our
concentric knockouts, maybe something like that.
And there could have been concentric. There could have been a 277. Matter of fact, let's make this brown. Let's make it orange and white, right? And then there could have been concentric knockouts, but there are no boxes with concentric knockouts.
No, they're listed even with.
Yeah, they're listed for this purpose. So this would have to be. We'll see in hazard classified locations. Let's just watch that. Well, here's a typical receptacle. So this grounding contactor receptacle is going to be bonded to the box, and this cover itself, or rather the threaded entries, that provides the bonding methods. So that's the general concept of bonding. But I want to bring out a couple other things to be aware of. And this is a comment, as you notice in the heading. This is not a rule. This is a comment. Let's follow the current here. Current leaves the power supply. It's in red. Travels to the meter enclosure. Travels to the main breaker. I like it's all red. Travels over to the panel board. And then it travels in red, travels out to the load. And at the load, there's a ground fault. And we talked about this, or we're going to talk about this now. When there's a ground fault, the ground fault current does not try to ground. It travels on the conductive parts. This is an equipment grounding conductor, which we'll talk about. And it continues on here. Maybe this was a piece of liquidite. And maybe this is a piece of PVC going out to that box there. And then maybe we ran some PVC from the panel over to the main disconnect, to the service disconnect. And then at the service disconnect, there's a main bonding jumper, which connects the enclosure to the neutral. And then, of course, the fault current continues on the neutral, travels on the neutral conductor, gets back over to the source. So what have we bonded here? We have bonded, and we'll see if we can maybe make these points a different color here somehow. We bonded this enclosure to this enclosure right here with this equipment grounding conductor. And then we bonded that enclosure to the panel. And then we bonded that enclosure to the panel. And then we bonded the enclosure to the neutral. That's bonding. Now this bonding right here, watch this, purpose is to connect two or more conductive objects together to ensure electrical continuity of the fault current. So we have bonding to carry fault current. Now look at the other type of bonding here. This is going to be in swimming pools. And swimming pools in 680.26b says all metal parts of a pool structure must be bonded together to minimize potential voltage differences between the conductive components. We're not trying to clear a fault here. All we're trying to do is tie everything together. We'll be talking about this when we get into 680. We're not trying to clear a fault. Rod.
It's the bird on the wire concept. You have the same potential as everything around you, so therefore there's no difference in potential.
Exactly. Tying everything together. And we'll talk more about that. But we're not trying to clear a fault. Is that right?
No.
Correct.
We're just touching it together. Okay. Now let's talk about a supply side bonding jumper. Now, I know that when you get into the definitions, it's like, please try to stay focused. I'm trying to pick only the definitions I think on the video that really matter. We talk about bonding. One is to carry fault, one is to bring everything to the same potential. Now we're talking about the supply side bonding jumper. Let's take a look at this word. And I don't know how I can describe a better way to describe this. You see right here, we need to show a fault here. If there was a fault in this raceway here, the fault is occurring on the supply side of that protection device. So if there is a fault that occurring inside here, we can see the fault would then travel with arrows along this conductor that would take us there. So therefore, this is going to be on the supply. So this fault right here is taking the fault on the supply side. So this is occurring before the overcurrent protection. So therefore, it's a supply side bonding jumper. Supply side bonding jumper right here. Eric?
And you might want to show that fault in two directions because some of the fault current will go through that bonding jumper to that neutral block in the disconnect, but then some others are going to go through the nipple.
Yeah, not only that, but I mean, in reality, the fault current's traveling along here.
Right,
And it's going in there. The fault current traveling on the enclosure, coming over here, returning on the neutral. So it's kind of like, if I show any current, maybe I should show no current at all. Talk about it, but it's on the supply side. Now, you also have a supply side bonding jumper at a transformer. Now, I know this is really busy. Let's take the current. Current is a secondary winding, goes to the disconnecting means, travels to the, current, we got to remove this current right here, Mike, on the black. Current leaves the secondary winding, travels to the overcurrent protection, travels over to this location, and then there's a ground fault. Fault current travels on the enclosure, and then we have what? We bond this right here. Now we have an equipment grounding conductor, and now we bond that enclosure in case there was a fault in that enclosure. Then we bring a supply side, and we need to bring this out in this graphic here. Somehow we need to, we have the point there. This is what we're talking about. This is the supply side bonding jumper, and the fault current goes back. If I had, let's see, so this is the supply side. That's the only way the current can get back over to that source. There's no overcurrent protection on these conductors here. And actually what I think I'd like to do is, I'd like to show this fault actually in the disconnect, not at the panel. So the fault should be here, happening before the protection device, and then the fault current would travel on the supply side. Yes, Eric?
So just one thing for folks, it's one definition, and you split it into the two to make it easier for folks to understand. But if they're looking for two definitions, you have supply side bonding jumper service, then you have supply side bonding jumper transformer. In the definition, it says service or separately derived system. Transformer is a separately derived system. So it's just so folks understand, there's not two definitions, there's one definition.
And let's go to the graphic. So in this definition, I say the conductor on the supply side of the service overcurrent protection device. Over here, the conductor supply side of the separately derived system overcurrent protection device. But in reality, the code would have said all the words were the same thing, except it would have said supply side of service overcurrent protection device or
separately
supply
derived
side
system.
separately derived system. So
Right.
I've split it up so people can understand that there's two different conditions,
But one definition.
but there's only one definition.
Right.
All right? Definition of a pressure connector, you know, I think it's understood. Device that establishes conductive connection between conductors or equipment, or between a conductor and a terminal by the means of a mechanical pressure. Brian.
And I just want to mention something. It's not necessarily compression crimp. It could be a Polaris tap, Ilsco connector, whatever you want to call it, but it doesn't have to be a crimp, because sometimes I forget when I see the compression. I'm always thinking, oh, it's got to be something that you're crimping onto a piece of wire.
Well, then you know what we'll do? We'll put a pressure connector, a set screw pressure connector on this. We'll put the compression and the set screw on the revised graphic.
Okay, good.
Then we can have them both, and then not showing one, because that can imply just one. Thank you. All right, now we have the definition of an effective ground fault current path. We talked about this a little bit. Let's watch this. Current leaves the power supply, travels through the meter, over to the main breaker, to the panel protection device, through the outlet, over to a load. There's a fault. It's called a ground fault, but the fault current's not going to ground. It's going back to the source. It travels on the equipment grounding conductor. And then we should throw the arrow to the equipment grounding conductor here. And then the equipment grounding conductor here. And then this is an equipment grounding conductor right here also, identified as an equipment grounding conductor. And then we have a main bonding jumper. And then the current travels back on the neutral conductor and goes back to the utility, because that's where the fault current. So that's the path. Now let's read the definition. An intentionally constructed, low impedance, electrically conductive path designed to carry fault current from the point of a ground fault to the supply source. So, interestingly, this neutral conductor is part of the effective ground fault current path. You know what I'd like to see? I'd like to see the code require the service neutral conductor to be white with green identification tape, because it's used for white to carry the unbalanced load, and it has green phase tape for the purpose of what? It's part of the effective ground fault current path. Now, the color green in 250.119, which we're going to get to, can only be used, and I'm wondering, can we put it on that neutral conductor that's on the service? Well, we'll hold that thought there. I think it can only be on a certain conductor, not the neutral. Brian.
I was just going to say, you know, the last few weeks as we've been getting ready for this, I have found myself going to the definitions a lot, because I've discovered that when I don't understand what's being said, it's usually because I don't understand the terms that are being used correctly. And I just want to encourage people that we're going through these definitions, but if you feel like you're not understanding what's being covered, do yourself a favor and look up the word that's being covered in the definitions, no matter where you're at in the code book.
Like I said earlier, it's so important that we understand the definitions, because this is going to be important as we go further. Scott, were you going to say something?
Yeah, I think Brian makes a great point there. And also, this is kind of a definition that people would probably ignore, but it's probably the most important definition for many of the things in Article 250, because current is returning to the source through lots of paths, but there has to be one that's effective. And effective means that it's the ability to clear the overcurrent device. This is a really critical definition that people overlook.
I think I went over this too fast. I'm going to go over it one more time, because this is everything, right? Yeah. This
Most
is
of
to
the rules in
prevent
250
electric shock. I talked about, if you watch the video section, about the purpose of the National Electric Code and people getting killed. The purpose what? There was a ground, I got goosebumps right now. There was a ground fault. There was no effective ground fault current path. Therefore, it remained energized. I need to have another graphic right after this one, Mike, and showing a lack of an effective ground fault current path. Everything is being energized, you get killed. So let's look at it one more time. Okay. We have current leaving the source, traveling to the meter, traveling to the main, travel to the panel, go to the overcurrent protection device. There is a ground fault, which means current's traveling to the source, travels on the equipment grounding conductor, travels on the equipment grounding conductor through the main bonding jumper, travels on the neutral conductor to get back to the source. This whole area that's shown as green is the effective ground fault current path. And if you have an effective ground fault current path, it will then have the low impedance, be electrically conductive, and it's designed to carry the fault current from the point of a ground fault to the source. That's it. I mean, we could stop right there without having to get, we could stop everything we're doing and say, okay, we're done. Because if we had an effective ground fault current path to everything, one paragraph, we don't have to have all of these rules to try to tell people how to maintain, how to create the effective ground fault current path. I'm not going to say that today's individuals, well, first of all, if you don't understand
The basics.
physics, right? Well, you don't understand how current flows. You're already, you're hurting yourself. And then if you don't understand how current flows like this here, then you don't understand how protection device works, then we're lost. So, Rod, did you want to say a quick one?
Just real quick, the laws of physics are strictly enforced.
Oh, the laws of physics are strictly enforced. That's a good one. All right, let's move on. Now, that was an effective ground fault current path supplied by the utility, right? Let's take another one, an example of the effective ground fault current path if you have your own transformer in-house. Current leads a transformer to the overcurrent device. There's a ground fault. Fault current travels on the equipment grounding conductor, travels on the supply side bonding jumper, and it returns back over to the source. Now, the supply side bonding jumper is in the event you had a fault on the line side of the protection device. And one of the streamers who's watching this program together with us, he say, well, wait a minute now. And I don't want to change this graphic here, but if you had a fault on the supply side, 1 second, this is the effective ground fault current path, is that right? Mm-hmm. If I had a fault right here, the effective ground fault current path would only be from the supply side bonding jumper to the system bonding, right?
Yeah.
It all depends where the fault is. And from that fault back to the source, it's the effective, okay? So now, Scott, we have a supply side bonding jumper here, a system bonding jumper there. We have the effective ground fault current path. Fault is taking place on the line side of that disconnect. And the comment is like, well, what are you going to do about that? I guess we're back to 90.1, the practical safeguardings of persons, because what can we do about that? It's on the line side. We can't not bond it. Right. So we got to bond it. We got to be able to carry fault. Yeah, but Mike, you're carrying. But there's nothing we can do about that. I'm assuming that if you had enough fault, Eric, you're the engineer here, is that if we had enough fault on, let's say, phase A, but the problem is that it's not going to be evenly distributed over to the primary side. Is there a way, Eric, if I put 600 amps on phase A fault, that you can calculate out how many amps is traveling to the primary? Because it's not going to be an even ratio because we're only taking up one winding. It isn't like it's a 2-wire in and 2-wire out.
Yeah, sure, you can do that. I mean, it's because when you look at the primary and the secondary, the delta and the Y, those phases are together. So there's one phase on the primary. For example, you have that highlighted phase right there on the secondary. Mm-hmm. Okay, you can highlight the corresponding phase on the primary.
Side,
yep.
Really?
Yeah.
Okay, yeah.
I'm not going to get it. So you're saying that then the primary protection device is going to pick up that fault on the secondary side, ultimately.
It depends on a lot of things, but yes.
It's a direct
If
reaction.
anything is going to pick up the fault
Right.
before the thing burns down, okay?
That's why
that would be the only one.
It depends. We did it in our shop one time. We got the primary to trip.
You did?
But not every time. But again, that's
Practical
the
safeguards.
only one, that's the only thing that's practical.
So, again, that doesn't mean you're not going to have a problem here. But we're doing the best we can, right?
Right.
All right, let's move on. So that was a good point. That's the effective ground fault current path with the transformer in the premises for the customer. Scott.
One small thing, I had this happen on a job recently. It's the supply side of the overcurrent device. I did have a person tell me, no, the supply side bonding jumper is on the primary of that transformer because it's a supply of the transformer. No, it's the supply side of the overcurrent device. Look at the definition. That's key.
Definition: an intentionally conducted low impedance electrically conductor path designed to carry fault current from the point of a ground fault to the supply source. So therefore, this is a supply side bonding jumper because it's taking it to the source, and the source is a secondary winding, not the primary side. The primary, if there was a fault in the primary, that's the purpose of that equipment
one,
grounding
right there.
conductor.
Right.
Yep.
I love these graphics. Okay, energized, definition. Electrically connected to a source of voltage. I don't have a graphic. If anybody has a graphic. Energized, connected source of voltage. Ground. I love this picture. The only thing I think it improved is have like a constellation in here. Maybe there is a constellation, but I think, Mike, you could put a constellation in here and then, maybe put the outline of a constellation. I like Leo, by the way, just saying. Or Orion's belt. I love, those are my constellations that I kind of like, my favorite ones. Just saying. All right, so ground is what? The earth. Now, from this point forward, I think we're all in agreement on the team. If you ever use the word ground, we're talking about what? The earth.
Soil.
The earth, the soil. The problem is sometimes in the code book, not so much panel 5, But those guys in chapter 3, in chapter 4, in chapter 5, they use the word ground. Matter of fact, we'll take a look at switches. I think it's 404.9. Oh my gosh. That is like the poster child. I always have a poster child of like the worst rule in the code. 404.9 has to be the poster child rule. Because they talk about everything in the world, and you're like, we don't even know what they're even talking about anymore after that. So, earth. So let's work with that. Ground fault. It's 125 years of people thinking you drive ground rods, but it really doesn't go to the earth. Let's read the definition, though. An unintentional electrically conductive connection between an ungrounded conductor, which is the hot wire, and the metal parts of the enclosure, raceway, or equipment. And all metal parts are bonded together. So theoretically, if all parts are bonded together, when you have a ground fault, you're going to clear the ground fault. Brian.
Well, actually, Scott and I, and actually a few of the guys, were talking about this exact thing last night. And the younger people in the trade will hear us that have been in the trade for a long time, and we'll be like, oh, yeah, put a ground wire over there. Or put a service over there. Well, these apprentices are like, wait a second. We don't need a ground wire over there. We need an equipment grounding conductor. What are you talking about? Well, we knew because we've been in the trade. So I just want to encourage the younger guys as we're going through this stuff, just because you know this, don't assume the people that you're talking to know this.
Oh, no, this is a major problem.
Yeah.
When I teach a class in bonding and grounding, I tell people, listen, when you leave this class, do not tell anybody anything I just taught you.
Yeah.
Because the guys have been in the trade for a long time that haven't been coming to finding out what's really going on in bonding and grounding. They're going to go crazy. They think ground rod's supposed to be everything, and you're supposed to make all these connections at panels, and it's like, oh my gosh, you need to be watching this video to realize. All right, that's a definition. Oh, Scott.
Yeah, just one thing. Ground fault is not the best word.
No.
But having struggled with definitions sometimes, no matter what we call it, the key is the definition, not the word.
Now, I like
think
that.
No matter what we call it, I've joked around, we'll call it a Hope fault, we'll call it a Stromberg fault, whatever we call it, someone has to teach, you guys who are instructors are going to have to teach the definition. We're going to have to learn a definition. So to go through the heartache of changing all the publications to use something other than ground fault, we might as well just let's educate ourselves on what the word means.
If we understand what a ground fault is, that's a fault to the enclosures. And what do you do with the enclosures? You bond them back over to the source.
Exactly.
Okay.
That's it. Doesn't matter what we call it.
Doesn't matter what we
The
call
key
it.
is the definition.
Here's an example of a ground fault. Current leads to source. Fault downstream. Current travels on the equipment grounding conductor, supply side bonding jumper, system bonding jumper. That's a ground fault. Return to the source. All right, let's take a look at this particular definition. It's a really important definition. Grounded or grounding, connected to ground or some conductive body that extends the ground connection. It's pretty vague and pretty broad. Now, we haven't really talked about this yet. We've established what ground is, the earth. Now, at times, we are going to ground things, which means we're going to connect them to the earth for a specific purpose, and we're going to talk about that. The problem is the earth doesn't come, you can't take a wire and stick it on the dirt. So now we have to put something in the dirt so we can then take the wire and connect it to. And there are different types of connections that you can put in the earth. They're called electrodes. And since we're going to be connecting it with a wire to this thing in the dirt that we're going to put in the dirt, it's called a grounding electrode. The wire we're going to run to that, it's going to be kind of not complicated. It's going to be a wire going to the grounding electrode that we put in the earth. That wire is called a grounding electrode conductor. So now, we have an electrode because we're going to connect to the earth. That's the best we can do. We're going to run a wire to it, a grounding electric conductor, and then we're going to connect that wire to something that needed to be grounded. So take a look right here. Without getting into details, rebar under certain conditions could be considered an electrode, which makes our connection to the earth. This steel is connected to the rebar. The steel is going to be grounded because it's going to be connected to the rebar. This grounding electroconductor is connecting it over to the steel, which is serving as a conductor, connecting it to the electrode.
Yes.
So therefore, this enclosure is connected to ground, which is what? The earth, or to some conductor body, which is this conductor, connecting it to the steel, using the steel as a conductor, connecting it to the electrode, because it's the electrode that's in the earth, which is our ground connection. That takes care of what is grounded. Now, we have a definition of what is called solidly grounded. Now, I remember when I was starting in the trade, I heard the word solidly grounded. I didn't understand what it meant. It's really simple. What does ground mean?
Earth.
The earth. So you're going to connect it to the earth. You're going to connect it with a wire. Well, if you connect something to the earth from a system, which we're going to get into right now, which is going to be a generator in certain cases, oftentimes transformers, and you connect it to the earth, then that's going to be a grounded system. Take a look at this example right here, having to do with a transformer and a system connected to earth. I probably would like to have a different kind of graphic here that would show the line diagrams a little easier, but right here you can see what? This XO is connected to, there's a conductor, right? That's connected to the steel, that's part of the conductor, that's ultimately connected to an electrode that is going to be considered a connection to the earth, which is ground. So the secondary winding of this transformer, we'll see this later on, we'll do more of this graphics here. The secondary winding is grounded, which means this is a solidly grounded, a system connected to earth, ground, without any resistors or impedance.
Right.
Now, there is something else beside a solidly grounded system, which we're going to be talking about later on, and there's no definition, which has to do with a resistive grounded system. And in that case, they would actually put a resistor in there, and we will be getting that on 250.36. So we have solidly grounded, and we talked about that. What does this course involve? 122.40, 122.08, 277.480. That means that you're taking your system and you're grounding it or connecting it, the ground connection to the earth. Well, here's my graphic I was just looking for. Solidly grounded system. This system right here, as a conductor, using the steel as a conductor, connecting over to my electrode. System connected to earth without any resistance or impedance. We're good with that, guys? And there's a purpose of solidly grounding. Now, we have an equipment grounding conductor. Now, the equipment grounding conductor, you have all these words. And for the longest time, we didn't have all these words. We just had wires in places, and then we just kind of made up things, and we were confused. They've done a great job in Panel 5, which handles Article 250. And they describe every little tiny part. It seems to me like there's one part we're missing. I think I'll figure out where it's at. All right, watch this. We know we have to clear a fault in the event of a ground fault. And how do you do that? You have to have an effective ground fault current path. It has a capacity to carry the current, has low impedance paths from the point of a fault back to the source. Let's look at the graphic here. So here is our effective ground fault current path all the way there, right? In that you have what? You have your system bonding jumper, which is the conductor that takes the system right there, which we haven't talked about yet. Then you have the supply side bonding jumper that we've talked about that. Because it's the supply side of protection. If you are on the load side of protection devices, they're not called supply side devices, right? This could be a load side bonding jumper, but it's not, because we've always had that wire. That's called the equipment grounding conductor. Now let's talk about what is the purpose of the equipment grounding conductor. The conductor path that provides a fault current path and connects normally non-current carrying metal parts of equipment together. Okay, one stop. A conductor path that provides ground fault. Okay, right here. This path right here is carrying ground fault current. Is that right? So therefore, it carries ground fault current. And it goes on. And connects non-current carrying metal parts of equipment together. Okay, so we're connecting all these parts together. See right here? They're connecting it all together. And to the system neutral conductor. And all this gets connected here. And guess what? Connected over to the system neutral conductor or to the grounding electrode or both. I don't even know where you could have an equipment grounding conductor. Well, I don't know how you can get it to the earth, because this equipment grounding, here, it connects right here, and then right here, the grounding electrode can get. So yeah, that definition, it can work there. So this is the part right here. It connects parts together, and it also provides a fault current path. But it's only one piece of the effective ground fault current path. And Scott, you said earlier, it's that effective ground fault current path that handles the supply side bondage of the system bondage of the supply side, the equipment grounding conductor. You put them all together, we have an effective ground fault current path. All right, now let's talk about, Scott.
I was just going to say real quick that this is a really good slide that shows you all of the conductors. And so if you are confused on the definitions, you know, Mike's got them, they're all labeled, everything. This is a great slide if you're confused to go back to this slide.
Yep. All right, let's talk about, okay, now we know what it looks like as far as in the context of the effective ground fault current path. What is it in reality? Well, you know what? You get PVC, you pull a wire in it. The rigid conduit itself serves as it. The intermediate metal conduit serves as it. The EMT serves as it. 250.118 says flex can, and we'll talk about that under conditions. Liquid type metal can under conditions. If you have Romex, NM cable, well, you're going to have an equipment grounding conductor, bare. MC cable, traditional MC cable will have an equipment grounding conductor. MC all-purpose cable, well, that means the outer sheath of the cable itself is listed as an equipment grounding conductor. We need to point to that cable itself. That's listed as an equipment grounding conductor. Armor cable, put arrow to the cable. The outer sheath of that cable itself is listed as an equipment grounding conductor. So there's a lot of different types, and we'll cover all of them in 250.118. Not right now. Just kind of let people know. But Scott, what you said, the effective ground fault current path is everything. We fail by having an equipment grounding conductor that has not made a connection, like that young boy that's swimming in that pool. Everything else we've done.
Doesn't matter.
Everything you've done, what does it matter? Yeah, you strapped it within 3 feet, right? Yeah, you made sure you had a 1/4-inch gap when you put that on an outside wall. You did all these mechanical things, and you forgot to put the pressure connector, which is a wire nut, another one, under that one wire, and then you killed somebody. All right, anybody else comments? All right, let's go on. Now, next definition of grounding electrode. I mentioned to you earlier that the earth is ground. But since we can't take a wire directly to earth, we have to have something in the earth that we can connect a wire to that has enough surface area that can make enough contact to the earth. And we've established that, you know, metal water pipe under certain conditions can be, but then you have to be supplemented. A concrete encased electrode, that's a rebar under conditions. A ring around a building, that's number 3. You know, you can put a ring around a building. That's another conditions you could. Some ground rods, you know, that's number 4. Yeah, that's and then other listed electrode. And these are manufactured electrodes where somebody, well, I don't want to get the details, but there's other type of electrodes which we'll talk about when we get into 250.50 and 52 and 53. So that's our connection to the earth. Earth doesn't come with terminals. We got to put something in there so we can connect that wire to it. Let's talk about the grounding electrode conductor. I've kind of talked about this earlier. If we know we have an electrode, which is the concrete encased or the rebar, that's your electrode. The wire that's going to go to your electrode is your grounding electrode conductor. And you'll find out as we go along here, you're going to have a grounding electrode conductor for the service equipment, for equipment grounding. You're going to have a grounding electrode conductor connected to a grounding electrode for separately drive systems. And if you have a remote building supplied by a feeder, you need to have a grounding electrode to that remote building. We don't need that inter-system bonding termination in that particular graphic over there, but we do need to have it at the service, which we have. Okay, identified. This is a really important term. Identified doesn't mean approved, and identified doesn't mean listed. It means that the manufacturer specifically said, hey, this thing could be used for this application. It's not listed for the application because there's no listing standard. So somebody made up something. Let's take a look at this graphic right here. This particular ILSCO compression fitting is designed to be for 4/0 gauge wire, 4/0. However, if you have finely stranded conductors, see, finely stranded conductors are not permitted to be placed under a terminal unless the terminal is specifically identified for finely stranded conductors. And if you see the 3/0 flex fitting right here, that means that this fitting is specifically identified to be able to use for flex conductors, which is your finely stranded conductors. So recognize, okay, identified as what? Recognize as suitable for a specific purpose, function, or environment by listing, labeling, or other means approved by the authority having jurisdiction. So you go into a catalog, and it says you can use this for this purpose. Well, if it's not listed, that probably means that there is no standard to list it, but somebody made up something that could be used for that purpose there. Next graphic, important one, inter-system bonding termination. That's at typically the service or a building supplied by a feeder where communication systems is going to be used. 250.94, you're going to put this device right here. It provides a means to connect inter-system bonding conductors for communication systems to the grounding electrode. So I think I'd label this right here CATV, and I think I'd label this right here telephone. So now you're taking the telephone and you're doing what? You're connecting it to the inter-system bonding terminal, which is what? It's bonding. You're taking your grounding discharge unit right here, that is going to be for cable, which is 820, and you're going to connect it to the inter-system bonding termination, which is going to be bonding. What have you done? You've taken the AC system and you've bonded it to all the communication systems. And the intent there is to be able to reduce differences of potential, which we will talk about on 250.94. So that is what an inter-system bonding termination is, and 250.94 gives us the rules and the specifications for that product. And here's what it looks like. And that's a nice looking picture. But that's an inter-system bonding termination. Labeled. Now, labeled is different than identified. Labeled means the actual label itself has a symbol, mark, or acceptable testing organization. And as Mike pointed out right here in the graphics, you can't see that, but right there it's built in. There's a label symbol here. This product is labeled. Here's a Canadian, is it? No. Yeah, CSA, Canadian Standard.
Yep.
Okay, so it's Canadian, UL, so, it's labeled. Now, the authority having jurisdiction is making the approval of equipment. Now, we haven't gotten the listing yet, did we? Okay, let me hold on. Let's just stop right there. We had identified, we had labeled, and now we're going to go to listing. Equipment or material included in a list published by testing laboratory acceptable to the authority having jurisdiction. Now, this product right here is labeled. It is identified for an application. And if I go online to ul.org, I will find out that this particular product is listed. That means it's in a list. Now, the NEC, the 17 version particularly, increased the requirements of products to be listed. They've been adding more and more and more shall be listed. Now, remember I talked about the approval of a product? The approval means what? Listing or the authority having jurisdiction?
Authority having jurisdiction.
The inspector said, yeah, that's cool, no problem. But when the code now is adding requirements that it shall be listed, the authority having jurisdiction can't approve something that's not listed. Because it said it shall be listed. Luminaires have to be listed. Signs have to be listed. NM cable has to be listed. PVC has to be listed. So therefore, the authority having jurisdiction doesn't have the authority. No. Now, they could take a listed product and say, I don't want you using that product. I want you to use somebody else's product. They could have that because they're not approving. But whatever they approve, it's going to have to be what? Listed. Listed means what? Go to a website, go to a list, and it's going to be there in today's practice. Neutral conductor. I think we all know what it looks like. It's a white wire. It's a conductor connected to the neutral point of a system that's intended to carry current under normal condition. A Y system is a white wire on a 120, 240 volt single phase system. It's a white wire. A delta high leg system. It's going to be the white wire. I don't want to get any deep on the side there, but in our course, in what I cover, I only cover 120, 120, 240, 120, 208, 277, 480, 277, 480. Every one of those systems are what? Solidly grounded. So every one of those systems will have a neutral. I'm not covering generally ungrounded systems, and I'm not covering corner grounded systems. So pretty much all the white wires are going to be neutrals. So the code, here's what I'm saying. Here's why I'm saying this. You see this white wire right here? See how it's connected to the earth? That means that white wire is what? Grounded. And over here in this two wire secondary, that secondary XO is what? Connect to the earth, it's grounded. And then over here in the delta high leg system, the XO is what? Grounded. So the code actually identifies this wire as a grounded conductor. So when you get to Article 200, they don't use the word neutral. They use the word grounded conductor. Because you could, which I don't show a graphic here, and I'm not going to show a graphic, you could take one corner of this delta and not connect the neutral there, but you could ground it on the corner here, and it's a corner grounded delta system, and then that wire would be a white wire. It's not a neutral. So I don't want to get too heavy inside here. I'm sorry, maybe I even started it But when we talk about a neutral, it's a white wire, like we all know what it is, and we're moving on. I don't use the word grounded conductor. I guess you know why I'm telling you that? Because when you go to your code book, you're going to be looking there and it says the grounded conductor. And then you look at my book and you're like, well, hey, how come he used the word neutral? Well, because I'm dealing with 122.40, 122.8, 277, 480. The code is dealing with what? Every possibility. So that's why I want you to know why I'm using the word neutral. To simple it down to what we deal with. The neutral point. Now, the neutral conductor, see, the conductor connects to the neutral point. Well, what the heck is a neutral point? The neutral point is the common point of a Y system. And that's where we'll be grounding those. Common point of a 3-wire system. So we've seen it earlier. PV system. The PV system, which is an interesting concept, it's the combination of all components and subsystems that convert solar energy into electrical energy for utilization equipment. Slight editorial change in the 2017 on that. It didn't really change anything other than this. Yeah, I probably should add another graphic on top of this one, Brian and Mike, and that would be showing that it comes off of that breaker. When you come off of that breaker and you supply the PV system, so it's where the PV system actually stops and includes the breaker that you're connecting, actually connects right here, to this enclosure right here. So it includes all the parts, including the breaker that you terminate in or the line side connection. So I'd like to show, in the book, we'll probably add a couple more graphics to kind of enhance that. But we're going to cover that in 690 anyhow. Okay, separately derived system, and this represents a lot of different type of systems, and the one I'm going to show you right now is a transformer. So the general definition is this: an electrical source, and by the way, you see the primary and you see the secondary, okay? It's the secondary that should be shaded, not the primary, because the separately derived system, and we should shade, Mike, at the same time, those conductors. Everything on these secondary sides should be shaded, because those conductors, that's what the secondary system is. The electrical source, other than service, the service is the electric utility here. We want to identify this up here as the service equipment right here. So the secondary winding, other than service, where there's no direct connection to circuit conductors of any other electrical source. So if you take a look at a secondary winding, there is magnetic coupling between the primary, but there's no direct electrical connection between the primary and the secondary. So this is going to be your typical transformer.
Okay, other than those established by grounding and bonding connections.
You know, I was trying to avoid that. I didn't want to talk about that. But Mike, your secondary, man, is connected to the case here, and that case is connected over here with the equipment grounding conductor, which is connected to the case here. And so, therefore, that ultimately is going to be connected at the primary, and there is a connection between the secondary winding and the primary winding, the primary supply system, because the primary supply system is connected to the equipment grounding conductor, which the secondary is connected to the equipment grounding conductor. And what I used to teach on separately derived system is forget about any connections. Let's just establish whether it's separately derived. Then if it is separately derived, then this is what you do. But when you usually look at separately derived systems, you already see it already connected. And now you're saying, well, now that it's connected, well, not separately derived anymore because now it's connected to another system. So they added that a few code cycles in the past, other than those established by grounding and bonding connections. So you're looking at line 1, line 2, line 3. These conductors right here have no direct connection at all between line 1, line 2, and line 3 in the primary. We don't worry about bonding and grounding connections or earth connections. Scott?
Yeah, so this is clearly separately derived. As far as the transformer goes, a buck boost transformer is typically not separately derived because the primary and secondary do have wiring that is connected. Thus, it's not separately derived.
Okay. All right. Now let's talk about a generator. If you have a generator and you're switching to neutral, and I love the way this is shaded here, because clearly this system here has no direct connection to the system coming in here. Maybe we can shade the other system a different color, Mike. And so therefore you can clearly see that the yellow shade has no connection at all with the other section. So this generator is separately derived. Just trying to establish a definition. Now, if we bring a service and there's a neutral here, and we have a generator, and there's no neutral that connects at all to the loads, Well, then if you take a look at, I love the shading in here, Mike. The shading here, you can see there's no connection between the shading here and the shading over here. So therefore, this is also separately derived. Now, I know it's a struggle when I'm just talking about something like this here without the context. Bear with me. This is critical. Separately derived transformer. Okay, standard transformer, separately derived. You get a generator and you switch to neutral. That means that the neutral is not interconnected at all, so it's separately derived. You get a generator and you don't even bring a neutral at all to the transfer switch. Well, that means that that is separately derived. Scott.
Yeah, so people might think, wow, you know, this never happens. You always have a neutral. But that's not true. In most commercial buildings, this is a very common situation with the fire pump. And it's not even a transfer switch we supply. That fire pump transfer switch comes with the fire pump. So people need to be careful to remember that. So fire pump, separately derived system.
Hold on. You're telling me because the fire pump is a phase-to-phase load, we're not bringing a neutral to the fire pump.
Correct.
So since there is no neutral going to the fire pump, that means there's no neutral at the transfer switch, which means that it is that generator now is a separately derived system.
Yes.
Automatically.
Yes.
And then we have to do things if that's the case.
Yeah.
Okay.
So where people get messed up is if they have 3-pole solid neutral transfer switch and a fire pump, now you're in trouble because you got one, you have to be separately derived, the other you're not. So that gets very tricky for people.
Okay, we'll talk more about
Sure
the details,
does.
but I
When we get
like
later.
that example why you would have a no neutral to a
Right.
transfer switch. Okay, now here's another example of a separately derived system. Just bringing in a
We-
generator.
Done a lot
There are
with
buildings and maybe,
JEA
Scott,
with
have you done any buildings where that the whole power is a generator?
generators like this.
Well,
I've had a
temporarily,
mini
sure. Sure, if
generator
you're doing an
out there
outage, you
with-
shut down, something along those lines, and you got to power it up. Construction trailer for a job site is very typical where you bring the generator up.
So it's separately derived. We just trying to
Absolutely.
establish the
Lift
definition.
stations,
Yep.
What we're
water
gonna do with it later on,
pumps.
we'll know. Here's another one now. This is probably 90% of most applications. And that is the generator goes to the transfer switch. This is a service-rated transfer switch. And there is a neutral from the generator brought to the transfer switch, and there's a neutral from the service being brought to the transfer switch. And you can see we need to change. We can see that the neutrals are interconnected, the same color. So therefore, what? It doesn't meet the definition. No direct electrical connection from the circuit conductors of one system to circuit conductors of the other system other than through the bonding and grounding connections. And we'll have to have this text changed to reflect the text about the service conductors. So that text right there has to have the text here other than service conductors on that other separately derived one with the neutral one, the non-neutral. Continue definitions. We're almost done here. Service. This is an important definition. People make a big mistake in not understanding what a service is. Let me tell you what I've heard in my experience. People would take a disconnecting means and run a feeder out to a remote building. And they say, well, you treat that like a service. And Scott, when you and I first got together, I did some seminars at your shop, you were confused because your inspectors were saying, well, the second that transformer, I need you to treat that like a service. And they need you to do all kinds of crazy bonding and grounding things. Well, no, it's a secondary of a transformer. It's a separately derived system. It's not a service. So we have to know what the service is, and let's read that definition of what a service is. The conductors and equipment that deliver electric energy from the utility to the wiring system of the premises, only from the electric utility. So generators will only be feeders, secondary transformers will only be feeders, and services comes from the electric utility only. Very important point. Service conductors. Now, this is a real subtle point, but you got to watch it. Listen to it. The conductors from the service point, that's where the utility is going to be. We need to make sure we add the definition of service point to the book, to the service disconnect. Now watch this. I'm making a connection here, load side connection. This is my service disconnect. I'm doing a line side connection, 705.12d for solar. So this is solar. And I'm connecting it here. These conductors right here are not service conductors. And if they're not service conductors, why are they not service conductors?
No utility.
They're not from the utility.
Because they don't terminate to the service disconnect.
Okay.
We need to make sure we have the definition of service disconnect in the book. The service disconnect is the main means of cutoff to the building. PV conductors connected on the line side are connected on the line side of service equipment. So they can't be service equipment. So how many disconnects can you have for a single service? What's the maximum number of
Six.
disconnects for a single
Six.
service? 6 per service.
Right.
If you connect the PV system on the line side of the service, how many disconnects can you have for the PV system? 690 for the PV system disconnects. You might not know this. 6. Because it's not a service. It's a connection ahead of the service. Now, that you connect ahead of the service, what are those conductors called? Remember, I mentioned to you there's something out there that they're not called anything. I guess you'd have to call them feeders because they're not branch circuits. They're not service conductors. See, if they were service conductors, they terminate into a service disconnect. They don't terminate into service disconnect because this is an inverter disconnect. Actually, this is the PV system disconnect, Mike. Well, let's change this to the PV system disconnect right here. Is what this is. So therefore, these conductors are not service conductors. Now watch what happens, Scott. You see this raceway right here? You see this enclosure right here? I cannot 250-94 bond either one of those two because it doesn't contain
250, 92.
92.
92.
I cannot
Yeah.
92 bond because
They're not
this is
service
not
raceways.
service conductors.
Yeah.
They're not raceways. So we'll talk more about this as we get along, but you can see how subtle points are a big deal. So 2020, Brian, let's make a note to maybe make something that it can terminate to whatever. Service
that-
equipment.
Is that
Rod?
language, Mike,
Say it
that
again?
strong where it says you can't do it, or is it just not there?
We're going to see. The answer is no, you cannot do it.
Okay,
But then we need to talk about where does it say you cannot do it?
do it, right, exactly.
Okay?
Right.
And really what it is 250.142
Right, okay.
because you can only do it at service equipment. Well, that's not service equipment. Because what's service equipment? Watch this. Look at this. Disconnects connected to the load and a service conductor. So we have to know what service conductors are. They terminate the service equipment. Intended to control and cut off the supply to the building or structure. So this enclosure right here is the service disconnect because it's intended to turn off the supply to the building or structure. The PV system is not intended to provide turn off any supply to the building structure because the PV system is actually a power supply. It's not a load. So our brain has to look a little bit different. So I don't want to get too detailed, but I just want us to understand service conductors are conductors that go to service equipment. Service equipment is the main means of cutoff to the building. So therefore, these would be service conductors, and that's service equipment. Now, I remember for the longest time, I'd go in an equipment room, you see all these meters and all these disconnects. I thought all that equipment was service equipment. Well, it's all those meters. Well, the meters have nothing to do with it. Service disconnect, service equipment ends, okay, service disconnect connected to the load and a service intended to control and cut off the service supply to the building. This 400 amp main, let's say, that is what turns off the power to the building. That's my service equipment. Because I need to know what service equipment is, and so what service conductors are, so later on we get into bonding and grounding, we have the right reference. Service point. Oh, we do have the graphic on service point. Now, this is an important one. Service point, in other words, where does the utility end and where does the customer begin? That's all that is. It doesn't have to be complicated. If you're running wires out to the utility transformer, then the service point is where? At the transformer. If the utility is bringing in conductors on the line side of your meter, well, then the service point ends at what? It begins on the load side of the meter. So it's a matter, or if the utility they have a handhold enclosure in a neighborhood somewhere, and then they pick up the different, the units inside the different dwelling units, well, then where is your service point? Your service point is going to be inside that specific handbox, because that's where they end. So it doesn't have to be complicated. I'm going to look at this really fast. Ready for this? Here's an underground box. Utility is in black. I don't know if we don't have a code anywhere here. We probably should say a legend here. Black is the utility wiring. It ends there. And now we have what? That's a service point. So these are what? Service conductors, right? Number 2, service conductors, a service point. And it terminates in what? Service equipment. After that, I don't care about that. That's now gets into other details. Now, it's possible, Eric, for sure, in your facility, your utility in an area that you're at is what, 138,000, and then they stop?
Comes in at 115. We distribute it at 15 kV.
So you get it at 115,000, the utility stops.
Right,
Then you pick up from there. Well, then that's your service point.
right.
All right, let's talk about the definition of special permission. written consent from the authority having jurisdiction. Hey, Sam, can you help me out here, this and that? I say, listen, Mike, listen, here's what I need you to do for me. You need to go get an engineer. You got to write it all up. You got to give me a request, and then I need to review it. I will then waiver the rule, 90.4, because I have the right to waiver the rule as long as it's just a safe, and then I will sign it and give you a letter back.
Yeah, we see that a lot. The building official signs off on it. They submit an AM&M, and it just goes through the process.
Because listen, the code can't cover every single possibility. I mean, it's practical safeguards, but yet unique situations like, wait a minute now, we need to do it this way. Like, okay, that's fine. But you need to be written. Okay, ungrounded system. We talked about a solidly grounded system. That's where the winding on the secondary, and this is great showing just the secondary side, where the secondary winding was grounded, which means it's connected to what? On the grounded system, the secondary winding was connected to what?
The earth.
The earth, right? It's connected to the earth. It's grounded. Well, an ungrounded system means that we don't touch the secondary winding. It's floating. I guess. Ooh, could I use the word a floating system? Or is that not a good thing to use in here? Ungrounded system floating? Right. Doesn't ring well?
Well, you can do that. Floating would seem to indicate somewhat of a looseness. You can look at an ungrounded system, kind of like bungee cords, and bungee cords are the capacitance of the cable.
But yeah, okay, let's get off of that one there. The engineer's like, go on, Eric, what else? And we're like, huh? Okay, there is actually, you guys can look this up for me. Maybe the streamers can look this up for me, or Don, my guy, can do this. There's something back, I think it might be in 445, or probably 445.20, where they talk about a bonded neutral system and an unbonded neutral system, and I think they have the paren word floating for the unbonded system. So I think there is a concept there, but we're not going to mess this up right now. But I'm just throwing that out there to you. Article 100. Is there any notes that you guys have on any definition I might have covered, or maybe something I said that you'd like to see me cover, or just kind of fill in the blanks? Rod.
You are good. Brand new, unbonded floating neutral generators.
445.20?
Yep. A.
A? Okay, I missed A. Eric?
Just want to mention when you talk about services that it's extremely important to realize or know that not all buildings have services. That's important to know. So if it is a service on a building, it's covered by Article 230. If it is a building fed by a feeder, it's covered by Article 225.
You know what? We got streamer Ravinda from New York says, Mike, what about if you have a 208 volt primary supplying a 480 volt secondary? You know where you can take a transformer, you can reverse it?
Right.
Mike, we need to get a graphic. And that's, instead of being a delta Y, it's going to be what? You're actually going to wire it from Y delta. There's nothing wrong with that. One second, we're going to get into we're going to get into that, but that is an unground. Matter of fact, right here, I need to show another graphic like this, Mike. Except I'm going to make it Y delta, and I'm going to have the primary going into the Y primary, and then this delta is going to go into the secondary, and that would be another example of an ungrounded system. So that would be separately derived. And I want to show on separately derives, Mike, I want to add another graphic in separately derives, right? Showing an ungrounded delta system as another separately derived example. So we get them all. Mr. Hardy.
Yeah, they do make transformers that'll do that are listed to be that way, but if you take a standard transformer and you want to backfeed it, you got to take the main or the system bonding jumper out, because now if you're going backwards, you got to take a system bonding jumper out. Otherwise, you've got a parallel neutral to equipment ground connection.
Well, we're going to need to get a graphic and make a note of that. Let's get a graphic of showing that in there. Yes.
So it's just easier to buy the transformer the right way.
Okay, hold on. Let's stop here. I'd rather hit it right now because I'm afraid we'll miss it later on. He's saying, listen, you can reverse a transformer, but the transformer has to be identified. Here's where identify comes inside here. And it will be identified for backfeed application. And he's saying, well, you have to remove the system bonding jumper, which you have no clue what he's talking about, which we will be talking about later. So let's hold this topic until then, unless there's a compelling reason for us to talk about it now. Shut that down, didn't I? But we're going to go to that. Yeah. But I want to be able to explain it to people.
The problem is because people watch that and they go, oh, I'll just feed this thing backwards. And
well,
they
we're
go,
going to talk about it.
Time
We're
out.
going to talk. There's a couple rules we got to watch for that. All right, ready? Yeah. Let's now go to 110. Just a couple of things in Article 110, requirements for electrical installations, approval of conductors and equipment, 110.2, the authority having jurisdiction must approve all electrical conductors and equipment. That's back in 90.4. The authority having jurisdiction is approval of equipment. 90.7, which talks about, which we probably should add in the book, and that is that the authority having jurisdiction really shouldn't be going in the inside of equipment and looking and determine whether or not the manufacturer wired it properly, because it's listed if it's listed products. 110.3, use and product listing of equipment. I'm only covering 110.3b, which says equipment must be installed and used in accordance with listing instructions, with instructions included in the listing or labeling. Now, we got to be careful here. What almost nobody is aware of this. When you get a box and you open it all up and it has all these instructions, that doesn't mean you have to comply with any of those at all. Because what you don't know is, read the rule again. Look at the graphic. Equipment must be installed and used in accordance with instructions included in the listing or labeling. In other words, when the manufacturer had submitted products, they had submitted instructions to UL, or the listing agency. They then approved those instructions. And then these guys take this out and then they start putting it in marketing and they start putting all kinds, and they add all kinds of stuff. I've seen people have instructions and things that are wrong. Well, because they didn't submit those instructions to the UL. So you will never know what you're supposed to do or not do unless you got with the listing and you found out what were the instructions that were submitted with the product. In other words, here is my breaker, and here are all my candies. Here are all the things that go with this. So you have to take that package. Then all of a sudden you get it, and you got this box with all kinds of things inside here, right? Well, these other things were never part of the listing and labeling instructions. Now, what do? Well, we don't have the information what the listing and labeling instructions were, so we kind of assumed that what came with the packaging, it must be the instructions. And that's what inspectors are going to be. The only time this really matters is if you really screw up and the instructions say something, you're trying to figure out, how do I get out of that? Contact the manufacturer and find out, well, what were the instructions you submitted? And you might find out, Okay, now let's assume the instructions are correct. This product right here is a special product that this is on a PV module that you're going to be connecting. This is an equipment grounding conductor. When you connect that equipment grounding conductor on the module, the instructions of the module will tell you what type of, this is called a weeb. And what this is I need to get like a better picture of that. And what that is it's a product that is designed that when you bolt this down, it takes the anodized aluminum and it breaks the aluminum bond connection, and then it breaks the bond on this particular fitting and this particular screw and a specific torque. That then makes this module bonded to this fitting so that you can take the equipment grounding conductor and you terminate this with a torque to make sure it's correct. You just can't take a lug and go get it and stick it on a piece of aluminum because aluminum is anodized. Brian.
I just got a comment in from Don since we're talking about this. He says the UL stated opinion are that all instructions that are provided by the manufacturers are the 110.3b required instructions.
Where does it say that at? Well, I know, but other than
Don,
Don saying that. So we
Don,
have to find out.
can you give us the source for that?
Okay, we'll have to talk about it later on as to what it is. Only because Don says that, read it again, Brian.
It is UL stated opinion that all instructions that are provided by the manufacturer are the required 110.3b instructions.
All right, read it again to me. Oh, wait, 1 second. It's UL stated opinion.
Yes.
Which means nothing to me. Because if I'm going to court, I don't care what UL thinks. The code says the listing and labeling instructions supplied with the listing of the product. But I would agree with UL. If I was going to be making a statement, I would say, it's my opinion that whatever they're giving you, you got to follow them. Because if I say that, then you never have to come to me and ask me for what the instructions are. And if I was an inspector, as a group, IEI, I'd say, well, whatever the instructions are there is our position that those are the ones that were listing and labeling instructions. And so therefore, we're not wasting our time on that. So I don't want you misunderstanding what somebody saying a position is to mean a fact of reality. But the rule is, so if you were UL, if you were IEI, what would you do? You know what it is? It's my position that those instructions are 110.3b. That's my position.
Right.
That's my intended position. Now, if you don't like that, guess what? you can then go find out actually what was product in there. But other than that, we're not going to sit there and try to help you. So I can see the whole picture there. All right, let's move on. So we're going to take the instructions. It's the IEI's position, it's UL's position that, hey, whatever's there, you're supposed to comply with that. But if you're in trouble, then, of course, we get more information. 110.6, conductor sizes. You know what? No big deal to cover about this other than there are many tables that give you conductor sizing. And, you know, almost sometimes you have like the special code, and this is one of those special codes. See if I'm wrong. I've been doing teaching for 41 years. If you ask me what size wire is bigger than a 1, I have to think.
Yep.
I have to think. Bigger than a 1. Okay, it's not a 2, because 2 actually is smaller. It's a bigger number. Even though it's a bigger number, it's actually a smaller wire. And so bigger than a 1, okay, that's a 1/0. Now, I have no problem. 1/0, 2/0, 3/0, 4/0, 250, 5/0. I got no problem there. It's anything that's going to be from 1 gauge and lower, I have to think. Now, the reason you have all these different sizes, or any from 1, 2, 3, 4, do you know why it's a 1, 2, 3, 4, 5, 6, 7? Because when it made steel, they ran it through the first one. That was a certain size steel. It was a 1. Then they took that steel and they ran it through a thing that made it a little smaller steel, right? That was the second die they ran through. In the third, the fourth, the fifth, the sixth, that was 18 dies they would have run through to get the different size steels. So when it comes time for the wire sizing, I mean, come on, the guys making steel, probably the guys start making wire. So then they just would use that same following numerical. It's a number of things, the rollers that it takes that can compress that thing down, and that's where it comes from. All right, so that's your wire sizes. And you go American wire gauge, and you go to aughts. They can also be knots, N-A-U-G-H-T, but we use aughts. And then we go to 250. And I don't know the history, 1, 2, 3, 4. I guess like, hey, can you give me something bigger? It's 1 bigger than 1, so I guess it's 1, 0. Because you had a 1 and you had a 1, 0. I want a bigger one. Oh, well, we had a 1, 0, then let's make it a 2, 0, and a 3, 0, and a 4, 0. And then it's like, okay, well, we can't make it 5. How about I will make a 250, 500,000s. And the large wire that I'm aware of, I've had it, a 2 million circular mill conductor. I had it in my class one time. And it's used for DC power because a large wire, you can't use it for AC power because of other factors. But it was DC power for the exciter for a power plant, DC current. So that's where it came from. And I had it about a 5-foot piece. It's like about 75 pounds. And then somehow it disappeared.
Hey, Mike.
All right. Yes, Eric?
I was actually involved in a project that had 4 2000s parallel per phase.
4 2000s.
4 2000s per phase. Went from a 15 MVA transformer to a piece of switchgear.
Wow. Was it DC?
It was AC, but it was 4 aluminum 2000s per phase.
4 aluminum 2000 per phase. Wow.
It's a big wire.
Big wire. Section 110.7, wire integrity. You know, I didn't really want to cover this slide and graphic. Here's my ground fault. And, okay. That would be a ground fault. Well, let's read the definition. All wiring must be installed so as to be free from short circuits. Okay, here's my short circuits. Ground faults, we know what a ground fault is right there, face to the enclosure. And any connections to ground. Ooh, a connection to ground unless permitted. Oh, this connection right here, see, my neutral is bonded at my disconnect. This neutral is bonded at the panel, and that is a code violation. So therefore, this would violate 90.7 because it says any connection to ground, any connection, which would not be the ungrounded conductors, because we already talked about those to ground. That's a ground fault, right? We're talking about any ground faults, and then any connection would be the neutral conductor connecting to the ground. Not really ground, but, ground. Come on, we can work with ground being the equipment grounding conductor. These guys are not panel 5 guys. So that would also be considered a violation 110.7. Brian, do you want to say anything at all about that?
Well, I think I'm the one that actually asked you to put this in, and it's because a lot of people don't realize that the code does require you to have a properly operable installation. People are always like, oh yeah, it doesn't have to work, it's just got to be installed. Well, no, it does. It can't have short circuits. You can't have short circuits all over the place and expect to pass an inspection. It has to be free from shorts, free from ground faults. The code does require it. It is a code requirement.
Yeah, we know this is a code violation. We have a code rule on that one.
Right.
But a ground fault, there's nothing in the code says you can't have a ground fault and then get a final.
Exactly.
But it does now.
It does
not
now.
But I mean,
Well, yeah, right.
110.7 says you can't do that. All right, that makes total sense. Section 110.12, mechanical execution of work. You know, it's not a big one here. It's just that electrical equipment must be installed in a neat and workmanship-like manner. And I love this graphic. One of the guys gave it to me. And here's your metal raceways and bonding the ends of the raceway, and it's just a beautiful installation here. And what's neat workmanship like? I think inspectors, when they're inspecting jobs and they have this guy that does such a terrible job, I mean, the worst job in the world, they don't care what he does. They just want to get the final inspection and get him out of there. They'll allow anything almost to get done, just as long as it's safe. Where somebody who's a quality contractor, and he's a quality contractor, hey, that was 3 feet 1 inch away, so I had to turn you down. In other words, when you expect something from a higher performance person, you kind of get beat up a little bit more than the guy that's not doing such a great of a job. So it's a judgment call. That's the way it works. 110.14, conductor termination and splicing. Big deal to me. This is a big deal to me. Conductor termination and splicing devices must be identified for the conductive material. In other words, is it suitable for copper? For aluminum, copper-clad aluminum, and they must be properly installed. So here's the rule that tells you not only do you have to have them, but you got to install them properly, and they have to be properly used. So these are what, pressure connectors right here? Oh, here's some pressure connectors. We need to get the twist on, and we need to get these pushed right here. These are all, here's a pressure, is that a pressure connector? That's a pressure connector there also.
And Mike?
Yes.
Also, this graphic indicates the push-in type connectors. Be careful on those because they've got different voltage ratings on them.
Yep.
And so when you go for an inspection, sometimes if you just look at one side, you might think it's a violation because it's got the wrong voltage, but they're dual rated.
Okay. Here's an example. This, I don't know if you can see it or not. This is copper, Cu, 90 degrees C, so it's a 90 degree C terminal, and it's aluminum. The range here, it looks like it's 6 gates at 350 kc mils, and the terminal's rated 250 amperes. We had a lot of information here, so know what we can do with it. We talked about finely stranded conductors back in the identified rule of definitions. This is the rule that says connectors and terminations for conductors more finely stranded than Class B and Class C. That you go to Chapter 9, Table 8, and they talk about the number of strands, must be identified for the conductor class. I think we moved to Chapter 9, Chapter 10, Table 10 right at that point right there. Must be identified for conductor class. Well, in other words, this is identified for finely stranded conductors. If you go to Chapter 9, Table 10 in the back of the code book, it gives you an example, and maybe you guys can pop it up real quick there. It takes you I think it gives you the wire size and it gives you number of strands and that kind of stuff. So you can see this is, I don't know what this is, but this is probably what they call diesel locomotive cable, DLO. A diesel locomotive cable cannot be used because that's not a code wiring method. Unless that wiring method has a dual rating. And that wiring method is probably going to be rated RHH/RHW, DMLO, diesel locomotive cable. Yes?
And that's actually probably like a type W cord.
That is correct.
Because a DLO would be individual conductors typically.
Well, it would be a type W, you'd have to go to 400.4 table. I think it's a type W flexible cable. Take a look at that. Take a look at that. I think it's 400.4. It would be a flexible cable W, which is commonly used, let's say, in marinas.
Yep.
Because it has some wonderful permissions on how you can use W cable that you could not use another wiring method on. Because you have a floating dock position here. You need wiring going out there. It's suitable, and the W is for that application. So if you're interested in any kind of flexible wiring method to be used in a wet location and sun exposure and heavy duty, go to 400.4 and look under W, and it's a pretty cool wiring method. Continuing, now we're in 110.14a, the terminations. We're talking about general rules. Now we're into the terminations of 14a. Unless marked otherwise, terminals are listed for only one wire. Now, a split bolt connector is listed for 2 conductors unless marked otherwise. And they are listed, Don, you correct me on there, they're listed for solid or stranded conductors, but stranded conductors not larger than, Don, is that 6 gauge?
Solid,
Not large.
not larger than 8.
Okay, so therefore I could not have a 6 gauge?
Can't have a 6 gauge.
Oh my gosh. Holy moly. We need to double check that. If that is Don is correct, that a split bolt connector cannot be used with a conductor 6 gauge and larger. I hate that word larger then that is probably a very common split bolt connection made in the solar industry.
It sure
Because they
is.
usually use 6 gauge wire, solid, for the bonding of their modules on their
Don't
arrays.
see nothing wrong
So
with
Brian,
it.
let's just double check that. And then if that is the case, this looks like a 6 gauge wire. And then I would have to show that this is a violation of 110.3b, right? And then I should not even use this graphic in my book because I'm just now explaining, but this is a 110.3b standard saying that you cannot use 6 gauge and larger solid.
It's definitely a number 8.
So this is a number 8.
Absolutely.
Okay, okay, exactly. That's the only way it would be permitted. And we're going to say it's an 8 gauge wire. Okay, let's talk about splicing. 110.14b, conductor splicing. Well, let's just talk about wire connectors. Wire connectors must be spliced by an identified splicing device. You know, wire connector is identified as an identified splicing device. You know, different people handle it differently. I'm sure different people in different organizations believe that all wires should be twisted together first before they put a wire connector on there. Some guys are like, I don't think so. The product standard says this, and it's on the packaging. Here's the identification. Hold and strip wires together with the ends even, lead stranded wires slightly, pre-twist necessary.
Unnecessary.
Oh, pre-twisting unnecessary.
How many guys read the instructions?
So if you read the instructions, if you want to, of course, you know, you got to realize something. When the testing line, I've been to the Ideals factory many times, and I go in the rooms and they have all these wire connectors and they have all this current traveling in there, and they have all the thermal couplings and all the different things, and they're measuring every single thing, and it's heat cycling it on and off and on and off and on for whatever period of time. They don't twist the wires before they put on the wire connectors. They just put the wire connector, twist it on there, as it's supposed to be, and then they test it under those conditions. But I think our problem is we have a tendency, those of us in the field, is that maybe we we didn't have that red wire nut. And so we used the yellow one. And then, you know, when you're trying to get it started, okay, I got it, you know. Or, you know, it's not all the way in there, you know, you didn't hold it correctly because you're doing it while the whole box is energized, and so you're trying to carefully grab that, you know what I mean? And so these are all things that are like wrong things to do. Conductor torquing, 110.14d. This is a new rule in the 2017 code. This was an informational note, but in reality, this was a requirement via 110.3b. Equipment had to be installed according to listing and labeling instructions, and the instructions always required torquing. So they got the information about the torquing requirements in the UL standards, or the different standards. They brought that into the code book as an informational note saying, hey guys, you know, if the manufacturer has things marked on that, you kind of like got to follow the marking. And the people are saying, well, look, guys are not torquing because they're saying it's not required because it's an informational note. I said, no, it's required because, see, we're telling you it's a manufacturer instructions, and then you got to go to 110.3b, but by the time so the best thing is what? Take the informational note and just simply make it a requirement. So it took the requirement from the UL standard, or the product listing standards, into the code. Now let's read this. Where tightening torque values are indicated on equipment or installation instructions, a calibrated torque tool must be used to achieve the indicated torque value, unless the equipment manufacturer provides an alternative method of achieving the required torque. Now let me hit the last sentence first. In my experience, as I've talked to people, not many people are aware of this. Have you guys ever seen equipment that when you tighten it up, the head bolt breaks off? Well, that is the alternative method of achieving the required torque. And once you get it right, well, then that tool that's used, I mean, that portion of that screw is used is to get the torque, and then you stop at that point. Now, a calibrated tool is required. It's a big change. Not only did it change from informational to requirement, the requirements had also become beefier. What is a calibrated torque tool? Well, Brian, you've educated me that when you buy a tool, it's only good for 1 year of value, and after the one.
First of all, you have to buy a calibrated tool for starters. It's not just any tool you buy.
I can't go
is
to Home Depot
calibrated. No.
and Lowe's.
So, for instance,
Ooh.
we preferred the Klein tools because it was available easily at the supply house, not for any other reason. So you buy the Klein calibrated tools, and they actually have journeyman and master electrician tool sets with 2, 3, 4 different torque instruments in there. And it comes with a certificate that has the serial number of the calibrated tool on the certificate, and it tells you the expiration date of that calibration.
Okay. Now, you said, how much does something like that cost for a simple little thing?
Depending on the brand, but anywhere from $100 to $500
Wow.
per tool.
Okay. All right. So now, while we're here, anyhow, here's the torque information. If you look at this label here, the equipment grounding conductor can have what? 2 14s or 12s. So here's an example that on this terminal bar right here, you can put 2 equipment grounding conductors under a terminal. So remember we talked about 11014A, number conductor terminal, only one unless marked, identified otherwise. Here's the identification that it can have more than one. And all, of course, the branch circuit conductors are a single conductor, but this gives us our 2 conductors. Let's take a look at this graphic here. Let me see here. 3 to the 1/0, large, bar with 2 screws. Oh, it's a bar with 2 screws. The torque in pounds and inches is 50. Bars with 1 screw. Okay, so this will be coming out of a panel board, different kind of grounding bars. Here's again showing you the number of conductors. So here's our torque, depending upon the size of the screws.
Well, that's bars with 2 screw sizes. So some of your bars have big screw, small screw. And then some of the bars, all the screws are exactly the same size. So it's just differentiating for you.
Okay, so then if I had 2 screw sizes, it's going to be 40 pounds. But if it was a single screw,
40 on the big ones, 10 on the small ones.
oh, the large. Oh, I see it there. Oh, I knew that.
Yeah.
I knew that. Yeah. Okay, so if I had 2 screws of 2 different sizes,
Correct.
I need to get a picture of this. Then I'd put 40. Let's say for a 6-gauge wire, 45 pound inches for the large one, and 25 for the small one.
Right, and that's actually a very standard scenario.
Okay. All righty. Okay. Article. Yes, Rod. We're gonna.
Yeah, just real quick, Mike. In the absence of having a label on the equipment, you can always go to Informative Annex I in the back of the code book, and that'll give you some tightening torques for different types of mechanical fixtures and fasteners.
Great point. So what he's saying is that in addition, if you don't have that information you need there for whatever reason, you go to Informational Annex I, and it gives you some information as to general requirement.
Right.
Anybody have any final comments having to do with 110? We got some streamers that give us some questions. Ready for this? It says, I thought that the listed instructions is the basis for requiring of GFCI testing. Now, the instructions for the GFCI tells you what? You need to test it monthly. Is that right? Mm-hmm. But that doesn't apply to us because we are an installation standard. So the code doesn't require you to go out and test the GFCIs and to press the test and reset button. So that might be an instruction for the product, but it's not an instruction for the product on its installation. That's the instruction on its use.
Or maintenance.
Or maintenance, which is not the scope of the NEC.
Right.
It's
Okay.
a disclaimer.
Okay, the question has to do with what about the push-in connectors versus the twist-on connectors? When we saw about the push-in and twist-on connectors, I don't know. I haven't yet gotten enough of an industry feedback, even though it's been around for I remember when they first came out, the very first time they came out, I forgot who manufactured them. I didn't like them at all when they came out, and then they explained to me how the product worked. I've heard a lot of people tell me they love them. They push them in, they love them. And I've heard some people say, I don't like them. I got a feeling the people that I don't like them are the ones that have been twisting them all the time. You know what I mean? The ones that love them are like, I just get them a sticker right aside and I'm gone the next day and like that. You know what I mean? So, Brian.
I think the guys that don't like them are the guys that have been service contractors for a while, and they dealt with the experience of the backstab devices in the 80s going bad, and that really just gave you this bad impression of
That's the way
installing
it is with me.
conductors that way.
What
I'm gonna
Brian's
end
saying
it
is
right
back
there.
in the 80s, you could backstab a receptacle, and you can backstab up to 12-gauge wire.
We know
You try to
that don't
backstab
work.
a receptacle today, it only goes up to 14-gauge wire. And because it went up to 12 gauge wire, we had all that negative problems in the fires and that caused that left the imprint on that. Are you my mother? You know what I mean? They're like, oh, you must be my mother because it's the first thing I experienced. My rest of my life, I hate backstab. I don't care what they change. I hate aluminum wire. Yeah, but that was in the 80s. Why do you still hate it today? Well, I just don't like aluminum wire.
Still
Well,
don't work
The
good.
people that are starting today,
That's why.
they're pushing the backstabs. They're fine. Aluminum wire is fine because they don't have that historical, I hate GFCIs. Well, I know. Then you must have started in the 70s if you hate GFCIs. I hate
I did.
20 years from now, I hate AFCIs. That means you must have started when AFCIs came out in 1999. You know what I mean? So I know. So that's part of that history inside there. Next comment. Alexander says, fine strand carries more amperes than thick strand. The answer is false. Finely stranded conductors or thick stranded conductors do not carry any more current because it's still the same. If it's a 6 gauge wire, it is a 6 gauge wire and it has wire sizes are measured.
All right, I'm going to end it right there. I know that was long. We're trying to get caught up here. And if you would, just watch these videos. They're useful and they're informational. And then start on and try to complete the 47 questions behind the chapters, the practice questions. And I will see you next week. Y'all work safe.